Okay, so we are still working with U substitutions. So same unit here. Unit number 6, lesson number 5. We'll be trying to find an integral using the U substitution, but a little bit of a twist today. They're going to be definite integrals. All right, so that's where we go from left to right, and we have a starting point and an end point. So we integrate, from like 0 to 5, or we integrate from 2 to 7, or whatever the case may be. And so we're going to have to change the limits of integration, right? So instead of having the plus c, we're going to actually have a numerical evaluation at the end. But then one nice thing about this is that normally when we do a U substitution, after we integrate, we have to do the back substitution to the original variable. We don't have to do that because we're going to change the limits of the integration. All right, so the good old U substitution, you've got something like tangent to the 7th power of x. Oh, if there's some way of getting rid of a big ugly mess and just having a nice U instead. All right, so let's move forward and see what's shaking here. Okay, so here is a first example. I believe I got 3 examples set up. We're going to find the integral from 0 to pi over 2 of cosine of x over 1 plus sine of x dx. Right? So I got to take a look in there and ask myself, well, what would be the most useful thing to have u set equal to? And I'm like, well, the derivative of sine is cosine. And so I might be tempted to make u sine of x, but then I'm going to have 1 plus u in the denominator, and I don't know what to do with that. So instead of having u equal sine of x, I'm going to have u equal 1 plus sine of x. Right, now again, this is a definite integral because we're going from 0 to pi over 2. So we're not going to have a plus c. Right, we're going to need a numerical result at the end. So I'm thinking, okay, 1 plus sine of x would be the best use for u, because that way the entire denominator of that fraction is just going to be u. And of course, if I take the derivative of u with respect to x, the derivative of 1 plus sine of x becomes cosine of x. So my du is just going to be cosine of x dx. You'll notice I'm not showing that extra step where I multiply both sides of the equation by dx. I'm figuring by this point in time you're kind of catching on to some of those little steps where you don't have to show every single thing in total detail. All right, now the issue though is that because I'm now going to rewrite this in terms of u, my limits of integration are going to be a little bit different. I'm not going to be going from 0 to pi over 2 anymore. Right? I need to adjust those because I'm not going to be using x anymore. Instead, I'll be using u. And you ask, well, what is u? Well, u is 1 plus sine of x. So when x was 0, what would be the value for u? Well, it'd be 1 plus sine of 0. Sine of 0, of course, is 0. 1 plus 0 is 1. So my left point is going to be a 1. Remember, we integrate going from left to right on the graph. U equals 1 plus sine of x. Well, if we're going to go up to pi over 2, u is going to be 1 plus sine of pi over 2. Sine of pi over 2, of course, is 1, right, because that's the top of the unit circle, as high as we can go. 1 plus 1 equals 2. So my integral is going to go from 1 to 2. The cosine of x dx is taken care of by the du. 1 plus sine of x, well, that's just going to be u. So let's integrate. And if I've got 1 over u du, and I want to integrate that, what do I get? Natural log of u. But then, of course, I have to evaluate it at 2 and 1 and find the difference of those values. So I got to do natural log of 2, subtract natural log of 1, and of course, the natural log of 1 is 0. So I've got natural log of 2, subtract 0. So there's an exact answer, natural log of 2. Right? I do not have to back substitute into x at the end. I can just go with u. Notice I did not add the unit or the label square units because integration, well, we do a lot of things besides finding the area. Right? We can find volume, we can find surface area, we can find arc length, we can do all sorts of things. And so since this is out of context and I don't know what the integral is actually doing, I'm not going to label it as square units. Just end up with natural log of 2. Second example. I've got an integral that goes from 0 to pi over 4. Secant squared x tangent to the third power x dx. What should we let u be equal to? Well, I know the derivative of tangent is secant squared. So I'm going to let u equal tangent of x. Right? Derivative of tangent is secant squared. So the derivative of tangent of x will become secant squared x. So the secant squared x dx will be substituted with the du. Tangent to the third power u, tangent to the third power of x will just become u to the third power. Uh-oh. I gotta do some of those limits again. Right? If u is the tangent of x, when x is 0, the tangent is 0. Remember that sine divided by cosine. 0 divided by 1 will get me 0. When x is pi over 4, tangent of pi over 4, sine over cosine. Again, the nice thing about pi over 4 is that for sine over cosine, we're going to get a value of 1. Right? Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. Root 2 over 2 divided by root 2 over 2, of course, this is a 1. And so there's our integral. We're going to go from 0 to 1. The secant squared dx has been replaced with du. Tangent to the third power x has been replaced with u to the third power. When I integrate, I add 1 to the exponent to get the new exponent of 4. I have to divide by that new exponent. So I've got u to the 4th over 4. Evaluated at 1 and 0. So I've got 1 to the 4th power over 4. 1/4. A 0 to the 4th power over 4. 0 fourths. 1/4. Take away 0 fourths. 1/4. There's the answer. Third and final example of the day. Now again, at first glance, I might think that maybe, just maybe, I should let u equal 3x squared. But if I do that, I'm going to have square root of u plus 1. And I don't know how to integrate square root of u plus 1. I just want square root of u. So I'll let u equal 3x squared plus 1. Because when I take the derivative of u with respect to x, that becomes 6x. That matches beautifully what's already in the integral. So du will be 6x dx. Find the new limits. If x is 1, 1 squared is 1, 3 times 1 is 3, add 1, I get 4. When x was equal to 4, let's find the value of u. 4 squared is 16. 3 times 16 is 48. Add 1, you get 49. So the integral will now go from 4 to 49. The 6x dx has been substituted with a du. The 3x squared plus 1 has been substituted with a u. And so I just have to integrate square root of u du. Of course, when I see square root of u, I'm really looking at u to the 1/2 power. Add 1 to the exponent. I get 3/2. Divide by the new exponent. Of course, I never really want to divide with fractions, so I will instead multiply by the reciprocal. Right? So instead of dividing by 3/2, I'm going to multiply by 2/3. Let's do some plug and chug. Let's plug in those values and chug out an answer. 49 to the 3/2 power. Well, if I take the square root of 49, I get 7. 4 to the 3/2 power, well, square root of 4 is 2. Right? In the exponent, that denominator of 2 tells me take the square root. Square root of 49 became 7. Square root of 4 became 2. Aha, now the numerator of that exponent, which is all I have left now, 3, tells me to cube those. 7 times 7 is 49. 49 times 7, 343. 2 times 2 times 2 is 8. So it looks like I've got 686 thirds. Subtract 16 thirds. We'll run a special and call that 670 thirds. 670 is not a prime number, but it is not evenly divisible by 3. And so we will just leave it as 670 over 3. Oh, let's see what the aliens leave us this time. They're leaving us a message. It looks like we have a worksheet to work on. That's a sight you don't see every day, a flying cow. The UFO delivering things, that makes sense. The flying cow, that was a little bit unusual.